welcome to our AP pre-calculus video. I am Coach Meidenbauer, and we're going to tackle topic 2.11, which is logarithmic functions. Okay, so we're going to start talking about log functions here. And here's a general form, and we did review this a bit in the previous lesson in 2.10, but that's what the general form of a log looks like. It has a domain where all x values are bigger than 0. That's of the parent function, and then the range is going to be all real numbers. And then we're going to go ahead and sketch this, and then afterwards we'll talk about if we are concave up or concave down or what's going on with these things, okay, for increasing, decreasing. So just to kind of remind you how to sketch logs, and I'll do that over here, is when I look at my x and y values. For exponentials, I go -1, 0, 1 on the x's, but logs are inverses, so I'm going to do that on the y's. Okay, so when y is -1, x is going to produce a 1/2. When y is 0, x is going to produce a 1. When y is 1, x is going to produce a 2. So what happens when we double that, which is what I'm going to graph here, because this is 2 log base 3 of x. Oh, this is a base 3 too. What am I doing? Okay, base 3. Didn't read that. Not restarting. Just trying to see if you're paying attention. Sorry, it's base 3, so it should be 1/3 and a 3. And then when I double that, I should end up with -2, 0, and 2 over here. Okay. So at 1/3, I'm going to go down 2. So over 1/3, down 2 is right here. Over 1, up 0, and then I'm going to go over 1, 2, 3, and then up 2. Okay. So just take note, this is my x's over here, and this is my y coordinates right over here. And so this is going to produce a graph that looks like this. Please take note that we do have a vertical asymptote for logs right there at x equals 0. And if you notice, for this type of log right here, we are increasing. And the concavity for this one, they're asking specifically for concavity, and this is going to be concave down. Okay, moving on to this one. Okay, same idea here. I'm going to make my x and y chart. Okay, so -1, 0, and 1. So now my base is going to be 1/3, which is a wee bit different. So since the base is 1/3, we're going to get the 3 at the x value there for -1. X value here is still going to be 1, and this x value is going to be 1/3. And what happens when I take that and I double my y value? I'm going to get these values right here. Okay, so I'm going to go over 3, down 2, over 1, 0, and then over 1/3, up 2. If you notice right here, the shape did change because that base is now between 0 and 1. So it's going to make that now a decreasing function. So now we are decreasing, and we are concave up. Okay. There we go, example 1. Well, actually before that, let's talk about what the input and the output values of log functions do. The input values change proportionally as the output values increase in equal length intervals. Again, these only logs if our outputs also increase in equal lengths. I mentioned that in the previous video, so we can see it right there, right in front of you. Okay, so example 1 here. Given a table of values for a log function, show that the input values are proportional. So if you notice, all of my outputs are all just increasing by 1. And what are we having here from 1 over 25 to 1/5? If you don't know, you can just go, hey, 1/5 to 1. You still don't know. 1 to 5, we know that's a times 5. So all of these are going to be divided times 5. We just make this proportion A5. Looking over here at g of x, those are all the outputs are all increasing by 1, so they're equal length, and the x's here are all multiplying by 1/2. So you can see my proportion here is going to be 1/2. Okay. Okay, example 2, and this will kind of come into play a little bit when I get to the bottom examples right here, because there's a tricky one. So this one does have a transformation. This tells me that our transformation here is that we went left 5. So it's a horizontal translation by -5. So we're going to find the input values for f and explain how I know it's a log, even though the h does not have the input values that are proportional over equal lengths. Okay, so, well, what's happening here if I'm going +5? Like I told you, I'm going left 5. So if I go from this number right here to this number, and I had to go left 5, makes this blue number right here 81. Okay, so go from, remember, inputs are opposite. So usually we go from 81 and we, instead of adding 5, we're subtracting 5 because we're going from F to H. So do the same thing over here. Get 27, 9, was 3, and then 1. So how do I this? Is that this is a log because the input values are proportional over equal length output values. Okay. Actually, let's go to example 3, and then I'll hit up the example up here at last to end up with the limits. We'll talk about the end behavior part here in a second. So example 3, we're going to find our k values. We're told that these are logs. We know that these are logs. It says it right there in the problem. Let's find the values for k, which means that my input values are the things that are being proportional. 1 to 2, that's times 2. So this should also be times 2, which would make that number k equals 4. You can always check it if you want. 4 times 2 is 8. 8 times 2 is 16. Easy squeezy. First one right here, k to 6, I don't know, but I know from 6 to 18, that is definitely times 3. Times 3. So what times 3 gives you 6? That gives you a k equals 2. Skip that third one for right now. I'll come back to it because it's a little bit tougher. From e to the -2 to e, it's kind of weird. We have to know our exponent laws for this one. From e to k, that's kind of weird. K to e to the 7th. So since we're dealing with exponentials here, in order to multiply for exponentials, you're adding. What are we adding by every time? Well, to get from 7 to 10, we had to add 3 to the exponent, which means you're multiplying by e to the 3, which makes sense because we're multiplying by e to the 3 to go from e to the -2 to e. It's a mouthful. So to go from e to k has to be e to the 4. Just dealing with exponentials here. Oh, here's a great question here. It's logarithmic, if you notice. 4 times what gives you to 5? Well, that value ain't going to work from 5 to 7 and from 7 to k. It looks like that we have a problem that is similar to this one up here where we got a little bit of a transformation. Okay, so a couple ways to think about this is to kind of look and be like, okay, what's it changing by? So it's changing by 1 and then by 2. And then it'd be changing by, we're going to guess 4, and then it's going to change by 8 afterwards. We can also kind of notice here that if we shift everything left 3, so if we do x minus 3 to all of these, I'm going to get a 1, a 2, a 4, who knows, then a 16. We can clearly tell that this number between has to be an 8. So let's shift back. So k must be 11. Okay. Again, another way to do that one is to go from 4 to 5 is 1, from 5 to 7 is 2, 7 to what? And we know we're going to have to double it. So double 2 is 4. So 7 plus 4 is going to give us 11. I almost said 8. Okay, the very, very last thing here is for each exponential function, write the limits that describe the end behavior. So the end behavior for these are a little bit different. A log end behavior does not go to negative infinity. That's what's different about these guys. And that's what this little note says right here. Instead, we're going to be approaching 0 from the right. There are instances we're going to approach 0 from the left if it's a horizontally flipped or reflection over the your y-axis, it'll change. It won't be 0 to the right, it'll be 0 to the left, but all of these are going to be 0 to the right. So here they're just examples of graphs. All I'm going to do is just look at the graph and write down the limit notation. I'll do that in purple. Okay, so for this first one right here, the limit as x approaches 0 from the right of f of x, it's approaching the vertical asymptote downwards, so it's going to be negative infinity. If I'm looking at the right end behavior for logs, goes to infinity. So this is going to equal infinity because it's going up forever. Okay. Now, if all I do is I just do a transformation by reflecting over the x-axis, not much is going to change on the input side. So we're still going to approach 0 from the right, this time of g of x. From above, you can tell that we're going to now positive infinity, which makes sense that our end behaviors are going to completely flip. And then the limit as x approaches infinity, and it's going down forever, so it's going to go to negative infinity. Okay. Now, what happens when our bases are now smaller than 1, bigger than 0? Well, this is what happens. Okay, really not much of a change here between the upper right and the bottom left. They're actually pretty similar. We'll kind of get into that down the road. But looking at these limits right here, the limit as x approaches 0 from the right, which is my left end behavior for logs. Oh boy, I got shut out again. Really got to pay that electric bill. Let me pay it real quick. That's all I got to do to pay your electric bill, people. All right, we're going to positive infinity. And for h, as we go to the right side, we're going to negative infinity. Last one, and then I'm done. Why'd I write log? Nobody knows. So as you go from 0 to the right of k of x, we're going to approach negative infinity. Okay, because again, there's a vertical asymptote right there. And then the limit as x approaches infinity of k of x is going to give us a positive infinity. Okay, and that's going to wrap it up for our notes here for 2.11. Do not forget to like and subscribe.